Hello everyone. My goal in this video is to summarize what I've called birthday algorithms and Pollard row, and to show you both how these things work by writing it down, but also to show you some examples of it actually happening. Now, in the end, there's going to be a Pollard row algorithm for calculating discrete logs and a Pollard row algorithm for factoring. But the whole real idea of Pollard row actually doesn't have anything to do with factoring or with discrete logs. What Pollard row really is an idea of how to quickly identify collisions. And what a collision is two different things that have the same value. And exactly what the things are may well vary quite a bit depending on the algorithm or the context. So the reason why I've called these birthday algorithms is because the most common example of this that you'll give is how often it will happen that two people in a room have the same birthday. And so you might, for example, wonder, if there's 100 people in the room, what are the probability that two of them have the same birthday? And a lot of people's sort of gut reaction to that is, oh, it should be about a third, because 100 is about a third of 365. But this turns out to be wildly off, and in fact, the answer is very near 100%, that if you have 100 people in a room, that two of them will have the same birthday, or more. And indeed, in order to get to a 50% chance that two people in a room have the same birthday, you only actually have to get to 23 people. Now, at first this seems weird, because 23 is way less than 365, and in fact, the reason ultimately why we're going to be able to base algorithms off of this is because, yes, 23 is way less than 365. And indeed, the sort of key fact that underlies all of this is that you expect this sort of break-even number, where you're sort of like 50-50, to have two of the same thing, happens at actually somewhere on the order of the square root of the size of possibilities. So in other words, I'm saying there's 365 possible birthdays. This 23 actually is not of the order of 365. It's actually closer to the order of the square root of 365, which happens to be about 20. So here's a fairly precise version of this statement, which is more precise than the version I gave in class. So if items are drawn with replacement from a set of n total objects until I get to the point where I've drawn two duplicates, then the expected number of draws is going to this square root of pi n over 2 number, which square root of pi over 2 is about 1.25, so it's going to about 1.25 times the square root of n as n gets big. Now, I should note this expected here is in the probabilistic sense, meaning basically that if you did this a billion times and took the average of how many draws it took, this is the number you would get. So this number, for example, is definitely irrational. So when you say you expect to take that many draws, you're definitely not saying that you expect this because it's always going to be an integer. What you're saying is on average, it should be close to this. This is slightly different than the break-even point that's being defined up here. The break-even point that's being defined up here is really sort of a median, whereas this is a mean. But for this distribution, those things are close together, and if you count 1.25 times the square root of 365, you in fact get a number that's just a hair bigger than 23, so you end up really rather close to this 23 number. Now for us, we're going to actually be way less precise when we're using this. Namely, we're just going to always refer to this as O of square root of n. In other words, the amount of times that you have to draw grows not with n, but with the square root of n. Now, as a way of demonstrating what's really happening here, I wrote a couple example functions in Sage for us. And I'll go ahead and note these example functions that I wrote to show us this are posted to our class Sage folder. So if you want, they're under Pollard row examples there. So the first thing I want to do is just do an example of this birthday question that we were talking about. So I'm going to draw numbers here at random from 1 to 1,000. And the computer is going to just generate random numbers between 1 and 1,000, and it's going to do that until it generates a duplicate. So here you'll see the first number was 196, then 249, then 149, and it keeps doing this for a while. And you'll see the first duplicate is 781. And indeed, if you look just a little bit up, you can see it generated 781 right before generating this 781. And it helpfully tells us, hey, how long did it take in order to find that duplicate? That took 43 draws out of our bag. Now, of course, that's just one example. We can do this again. And we'll see this time, we found a duplicate after only 23 draws. Again, sort of strangely, the thing that got duplicated was said just shortly earlier. This time, it took 42 draws. And so this 107, the last one generated, was already in our list. It happened to have been right there. Now, pulling up our handy Wolfram Alpha calculator, we can see that 1.25 times the square root of 1,000 is about 40. So what this theorem I just wrote down is saying is that on average, the number of draws to get the duplicate should be about 40. But of course, it will happen that sometimes that number is way less than 40. So, for example, every once in a while, the second thing I draw out of the bag will exactly match the first thing I drew out of the bag, in which case I'll only take 2 draws. And also, sometimes I'll draw 900 things out of the bag and still not have any duplicates. But the average, that is, how long you should expect it to take, is about 40 draws. So what I have it doing now is not bothering to show us the actual numbers that are being drawn out of the bag, but instead only showing us the number of draws it took. So it has done here 20 different times this thing, and you'll see that in those 20 times, if you look at this, sometimes the number of draws is higher than 40, sometimes it's lower. The lowest in this case happened to be 5, which is actually quite low. And the highest is this one here where it is 69. We can do another 20, just if you want to see again how this works. And immediately this time, we actually beat our record from before. The first time it actually took 73 times to do this. And so if you want to play with this some more, you're plenty welcome to do so. But the basic idea here is that we should be able to find duplicates quickly relative to the size of the pool. Namely, the duplicates should happen after something like the square root number of draws. And so our hope here is to be able to write down some algorithms for discrete logs and factoring that are based on this fact. However, there is a problem with what I have just shown you. And the problem is actually only apparent if you look carefully at what the program I showed you is actually doing. And what the program I just showed you is actually doing is first draw a thing, then compare it to all the other things. If you find a duplicate, stop, else go back to the start. Now, this again looks like, okay, well, how many times am I going to have to go through these 4 steps? Well, I'm going to have to go through these 4 steps about the square root of n times. No problem so far. The problem is hidden in this step 2. Namely, the longer this takes, the longer this step is going to take, because comparing it to each of the other things requires one comparison for each other thing that it gets compared to. And so each time I go through this loop, I'm doing one more comparison than the last time I went through the loop. And so I'm the first time doing 1 comparison, then 2, then 3, then 4. And so you might rightly suspect that this thing here is actually growing quadratically in the number of times I'm going through this loop. And that's going to be a big problem, because the thing I was really happy about was that I was able to get the steps down from n to square root of n. But if you square root of n, you end up back at n. So here's the real problem, just summarized. The number of comparisons needed by this procedure is actually O of n, not O of square root of n. In order to demonstrate this, I thought it would be helpful to have the program actually tell you how many comparisons it's actually having to do for each of these runs through the program. And so if you look at this first run through the program, it happened to find the collision after just 36 draws, which is pretty good. It's less than the 1.25 times the square root of 1,000, less than the 40 we'd expect. But you'll see even then, even when you got this very small number of draws, it still actually took 630 comparisons before we found that collision. If we look at this slightly worse time, that is the second time through, where it took 48 draws, it actually took us more than 1,000 comparisons. And although most of these are ending up less than 1,000, you can see that every once in a while we miss high, and then this gets really out of hand. So for example, this is our worst one so far. It took 100 times for us to find a repeat, but that meant that this algorithm actually ended up doing 5,000 comparisons. And so what I hope you can see here is the number of draws isn't really the choke point for this algorithm. The choke point for this algorithm is actually the number of comparisons. Feel free to play around with this. Again, you want to convince yourself really of two things. One, of this fact that the number of draws to get a repetition is way smaller than the number. So you can even here use a way larger n if you want. So here, for example, instead of using n as 1,000, I'm using n as 1,000,000. And so you can do the square root of 1,000,000 as 1,000. So this should take about 1,250 draws on average. But you can see again, the numbers we're seeing are all many, many, many less than 1,000,000 when it comes to the number of draws. However, when we look at the number of comparisons, just like before, you see some things that are really high. So for example, this one is 2.5 million comparisons had to be done. So when I say the key idea behind Pollard row is a way of fixing this, it's a way of reducing the number of comparisons needed to identify a collision. But importantly, Pollard row isn't just going to magically somehow do this exact problem that we've been doing and find the matches quicker. Rather, Pollard row is going to fundamentally change the way in which we randomly generate our list of things, and once it's made that change, then with that new method of randomly generating things, it is going to be able to identify the collision much faster. So for Pollard row, the thing that's going to be different is that rather than generating a random number one at a time, we're instead going to generate a random function that goes from our space to itself. And what do I mean by our possibility space? I just mean the things that we were drawing out of before. So for most of the last example, the possibility space was the numbers from 1 to 1,000. In the birthday problem, the possibility space is the 365 days of the year. And in the most recent example, the possibility space was the numbers from 1 up to 1,000,000. Now, I have used the non-technical word random-ish because what's important here isn't really the fact that it is literally random. What is really important here is the fact that the function is not in some nice way related to the structure of the space. This is much more of an intuitive, you sort of know it when you see it kind of thing. And you'll see when we talk about the kinds of functions we're going to use, the kind of thing that works and the kind of thing that won't. But for now, I'm just going to black box what the function is. And I'm not going to think about what actually goes into the function. I'm just going to assume I have this function. I'm going to call that function f. So we've got our function f, and we're going to choose a starting point. And so, again, in our most recent example, this would just be a random number between 1 and a million. Once we've done that, the way I'm going to get my next number in my list is I'm just going to take f of x naught. So whatever this mysterious function f is, it starts in my possibility space and it gives me something back in my possibility space. So I'm just going to let x1 be f of x naught. And x2 is going to be f of x1. And x3 is going to be f of x2. And so on down the line. And so what happens is in this way, we get a random list of stuff out of the possibility space. This is the key difference between the way I'm setting things up for Pollard row versus the way I set it up for the birthday problem before. In the birthday problem, I was just independently generating a random element every time. But now, instead of doing that, I am generating the next element in a sort of algorithmic way from the previous one. In other words, this is in no sense random, because once the function f has been chosen, and the starting point x0 has been chosen, the rest of this sequence is completely determined. Namely, x1, again, is just f of x naught. And then, in order to get the next thing in the list, I just keep taking f again. So f of x1 is x2, f of x2 is x3, and so on. So this is really a recursively defined sequence. So if you want to think about something like the Fibonacci numbers, where you get the next term by adding the two previous ones, this is very much like that. Here's the birthday theorem again. Here we're talking about if items are drawn randomly with replacement, how many times it's going to take. This is not quite random, but here's what we hope. We hope that our function f is sufficiently strange, or sufficiently weird, that basically this list behaves in a way that is quote-unquote random enough that this theorem still applies. In other words, as long as we're careful that there's no mathematical reason why this sequence should do anything in particular, then we hope we can more or less apply the birthday theorem to it, even though it's not technically random. And I'm putting scare quotes around lots of words throughout this, because here when I say that random enough that the birthday theorem applies to it, in a literal sense, the birthday theorem never applies to a sequence that's not random, because the randomness of the sequence was a specific part of the hypotheses of the theorem. So when I say in quotes here, what I really mean is, I hope the conclusion works out the same. Before I go on and talk more about this, I want to give you an example of a function that is not random enough. So let's here imagine I'm working with the numbers from, say, 0 to 999. There's lots of functions I could think of there. Most of them are going to involve operations mod 1000, and it's perfectly fine to use operations mod 1000. And so you might think of something like add 1 mod 1000. And so you start at a random point, like let's say you start at 37. And so if f is add 1 mod 1000, then I start at 37. Next I write down 38, 39, 40, and so on. Here I am just constantly applying the add 1 function to the previous thing. Now, almost by definition here, it is going to take 1,000 steps before there's a collision. So in particular, if a collision is going to take 1,000 steps, that's nothing like what the birthday theorem promised. The birthday theorem promised it should be like the square root of the 1,000, and so I should be expecting, again, something in the neighborhood of 40, and I'm getting something that's 1,000 instead. And the reason for that is, again, the structure of this function very much connects with the structure of mod 1000. And so, if you take something that's too simple, add 1, multiply by 2, etc., you're very likely to find that your function actually does not get a collision anywhere near as quickly as you need it to in order for this algorithm to actually work. So, what do I use in this code we're about to see? The function I use does a few things. So the first thing is I round up the size of the space so that instead of working mod 1,000 or mod whatever number you input, we're always working mod a prime. So I'm just always going to pick a slightly bigger space so that we're always working mod a prime. This is really just so that my function doesn't accidentally develop any structure that works mod a divisor of the number I'm looking at, because there aren't any divisors of a prime other than 1 in the prime. I'm going to pick a random constant c that's going to be between 1 and p minus 1. You'll see it would not work well for it to be 0. And then what's my function here going to do? My function is going to take a number x, and it is going to define f of x to be x squared plus c mod p. So what's going to happen here is I am going to repeatedly square the number and add c. Square it, add c. Square it, add c. Square it, add c. And so let me just do an example here, mod, let's say, 23, just so that we understand what's happening here. Let's say p is 23. Let's say we get lucky and draw c equals 1, because that's a little easier for me to work with. And let's say our starting number happens to be 2. And so here, f of x is just x squared plus 1, some benign-looking calculus-y function. And so our sequence here starts off with x0, which is 2. And then the next thing I'm supposed to put here is 2 squared plus 1, which is 5. Now I'm supposed to put 5 squared plus 1. Well, what's 5 squared plus 1? Well, 5 squared is 25, plus 1 is 26, but mod 23 is 3. 3 squared is 9, 3 squared plus 1 is 10. 10 squared is 100, which mod 23 is 8, plus 1 is 9. 9 squared is 81, plus 1 is 82, mod 23 is 13. 13 squared is 169, plus 1 is 170. And mod 23, that works out to be 9. No, I didn't do that in my head. And now, here's the key thing about Pollard row. What is going to come after 9? Well, 13 is always going to come after 9, because how do I get the next thing after 9? I plug 9 into f, which gives me 81 plus 1 is 82, mod 23 is 13. And so we fall into this cycle, in this case a cycle of length 2, where I am repeating the same thing over and over again. So this ends up having, you could say, a period of 2, or an eventual period of 2, where it just ends up repeating 9, 13, 9, 13, 9, 13, and so on. So this part, maybe up to here, looks fairly arbitrary, random, whatever. I mean, it's not literally random, but this is just sort of a random mix of stuff mod 23. But then because of the deterministic nature of the way we've defined this sequence, it starts repeating in a very structured way. And so while the first part might look rather random, the end part definitely is not. It's forced to go into this cycle. And you might think about this. Why do I say it's forced to go into this cycle? Well, there's only 23 things that this function can be. And so eventually I have to repeat something. In this case, I eventually repeated the 9. But as soon as I repeat something, such as the 9, then I'm forced into this loop, because the second 9 is going to be followed by the same thing the first 9 was, and so on forever. And so it's always going to end up with this structure where it goes, okay, from something to something to something to something to something to something to something, and then back to something it's been before. But once it goes back to the thing it's been to before, it's going to repeat in a loop forever. And we don't know how long this loop is going to be. We just know it's always going to eventually fall into a loop. This picture is why this is called Pollard row, because row is the Greek letter that looks like that. And this shape is what underlies this entire algorithm. The fact that I'm going to start somewhere and sort of wander around this path, kind of at random, until I get back somewhere I've been, and then I'm going to be stuck in a loop forever. Now at this point, even though this is probably the second time you've seen me give this lecture, roughly speaking, we've probably completely lost track of what it is we're even trying to do here. But what we're trying to do is we're trying to identify collisions. Namely, I want to find two different spots in the sequence that are the same, like those two. And ideally, I want to be able to identify collisions in an amount of time that is more like square root of n than is like n. We know there should be a collision after something on the order of square root of n. We just can't find the collision in time that is proportional to square root of n, as of yet. But the hope is to use this mix where the first part is pretty random and the second part is highly structured to identify a collision. So when I was talking about the birthday problem, I used the word draw, meaning I'm going to pick a random thing out of this set, and I'm going to do that again and again and again. Whereas when I talk about this Pollard row setup, I use the word step. And I'm using the word step because by the time I'm implementing this, I've already fixed a function and fixed where everything is going to go. And so I'm really just taking a step on a set path. But the path, that's what this row is already set out before me before I even start. And this path just winds on forever and ever and ever. It just happens to repeat around this piece over and over and over forever. And so when I say step, I'm just saying one piece further along this path. So here's the key to how we're going to find the collision on this path. And so I'm going to have two characters involved. I'm going to have a rabbit, and I am going to have a turtle. And both of these are going to start at x0. In other words, on this infinite path that's laid out before us, both of them start at the beginning. Now, note, that's not actually a collision, even though the turtle and the rabbit are both looking at the same number, because, well, they're looking at literally the same place in my path. But what I'm going to do here is I am going to have the rabbit take 2 steps forward, and the turtle take 1 step forward. So, to start with, they're both looking at this. Then, the turtle takes 1 step forward. So I'll make the turtle green and the rabbit black. So the turtle is now looking at 5, and the rabbit is now looking at 3. Again, turtle took 1 step forward, the rabbit took 2 steps forward. Then I look and see if they're looking at the same number. And they're not. So the turtle takes 1 step forward. The turtle is now looking at the 3. The rabbit takes 2 steps forward. So the rabbit is now looking at the 9. And then they ask themselves, are the turtle and the rabbit looking at the same number? They are not. So then the turtle will go ahead and take 1 step forward. The rabbit will take 2 steps forward. Okay. The turtle's looking at a 10. The rabbit's looking at a 9. Those numbers are not the same, so we keep going. The turtle takes 1 step forward. The rabbit takes 2 steps forward. And now, the turtle is looking at a 9, and the rabbit is looking at a 9. And so we have identified a collision in the path. Now note, it's not the first collision in the path. It's just a collision in the path. So every iteration, I am going to move the rabbit 2 steps forward, the turtle 1 step forward, and then compare them. And note, if they're equal, we've found a collision. So in terms of statement, I think this is pretty straightforward. We have this path, the rabbit moves along the path twice as fast as the turtle. We keep looking at where they're facing, and eventually, when they're facing the same number, we stop, and then we've identified 2 points in our list that are the same. What's not at all clear is why this is a reasonable idea, and how long it's going to take, and I think it's not even clear at first that this thing is ever going to stop. That is, like, maybe the rabbit chases the turtle or the turtle chases the rabbit forever. And that would be bad. We certainly don't want to have an algorithm for doing something quickly that actually never stops. That would be a problem. But the key here, and hence the reason why the algorithm is named after this, is in the row shape of the path. Namely, eventually, both the rabbit and the turtle are stuck in a loop. And I have no idea where the rabbit and turtle are in the loop when they're both stuck in the loop. But eventually, they're both here. And so if this is the turtle, and somewhere else in the loop is the rabbit, then what's happening every iteration is the rabbit is moving twice along the circle, and the turtle is moving once. And the way I want you to think about this is that this circle here, this loop of the row, is a racetrack. And the rabbit is chasing down the turtle. Because every iteration, the rabbit moves forward 2, and the turtle moves forward 1. So if you think about it in terms of the gap between the rabbit and the turtle, what that's saying is every iteration, the rabbit closes the gap by 1 space. And so, however far behind the turtle the rabbit is, if the rabbit catches up by 1 space every time, then the rabbit will eventually catch the turtle. And in fact, if you actually know the gap between them, you know exactly how long it's going to take the rabbit to catch the turtle. Because in this case, for example, I've put the rabbit 1, 2, 3, 4, 5 spaces behind the turtle. So 5 iterations from here, the rabbit and turtle are going to be looking at the same number. This idea, the row shape that creates a racetrack where the rabbit chases the turtle and eventually catches the turtle, that is the fundamental idea behind Pollard row. And that is sort of the genius behind all of this. So because of the row shape, the first repetition is where the row closes. And as soon as the row closes, we now have a rabbit and a turtle stuck on this racetrack. And the length of the racetrack is an upper bound on how long it's going to take the rabbit to catch the turtle. Because again, the maximum gap that could possibly be between the turtle and the rabbit is the length of the racetrack. Well, if the first repetition happens k steps in, let's just call it k, that is to say, that's the kth step, right there, 1, 2, 3, 4, 5, 6, k, then the length of this loop is at most k, and so what you can convince yourself is that the rabbit and turtle are going to find this collision after at most 2k steps. Now, in a sense, this is a huge sacrifice, because we're saying if the first collision happens at, say, the 10,000th step, we're accepting that we might not find a collision until the 20,000th step. But that's okay, because again, we hope that the first collision should happen around the square root of the size of the number step. Okay, so putting this together, the birthday theorem gives us hope. Hope is the right word. But the birthday theorem gives us hope that the first collision should be somewhere around 1.25 times square root of n. So that's to say k should be somewhere around 1.25 times square root of n. And so then we find a collision at most twice that. And so, ultimately, what this is telling me is that I should find a collision in O of the square root of n iterations. And remember what an iteration is. An iteration is 2 steps for the rabbit, 1 step for the turtle, and 1 comparison. And so before, our problem was we were doing O of n comparisons, and that got out of hand. In other words, our problem was that as the algorithm went on for longer, every iteration of the algorithm took longer than the previous one. That is not true with the Pollard row algorithm. Every iteration here is exactly the same. 2 steps for the rabbit, 1 step for the turtle, 1 comparison. 2 steps for the rabbit, 1 step for the turtle, 1 comparison, and so on. And so, with Pollard row, as long as we get lucky enough that our function behaves random-ishly enough that we can count on this square root of n business, then we should find a collision in O of square root of n iterations, and in particular, O of square root of n comparisons. And so ultimately, this should be an algorithm that finds us a collision in an amount of work that is O of square root of n. This is a genuine improvement over the previous algorithm where we needed O of n work. And this O of square root of n is what's going to allow us to factor and take discrete logs more quickly. Now, in hopes of making that clearer, let me try and have Sage run a demonstration of this for you. So we have a path, and over on the right, I am recording what step of the path the turtle is on and the rabbit is on, and what number they're looking at. So you can see they happen to both start at 421. Remember, the turtle and the rabbit are always going to start in the same place. The next line is the next iteration. And in that iteration, the turtle is now looking at 380, and the rabbit is now looking at 836. Again, the turtle moved forward 1, so the turtle's now on the first step of the path, and the rabbit moved forward 2, so the rabbit is now on the second step of the path. The next iteration, the turtle is now on step 2 of the path, looking at the number 836, which might look familiar because the rabbit last iteration was looking at 836, because, again, the rabbit last iteration was looking at the second step on the path. But the rabbit now is on the fourth step of the path, and the rabbit is now looking at 342. And so any old number you pick, like let's just pick this random number here, the rabbit is here 11 iterations in at the 22nd step, looking at 858. Well, when is the turtle going to make it to this step? The turtle is going to make it to this step 11 iterations later, at iteration 22. And indeed, 11 iterations later, at iteration 22, you can see the turtle is indeed looking at 858. So it's important to remember here, the turtle and the rabbit are walking the same path at different speeds, but they're looking at the same numbers. And so, every number the rabbit sees, the turtle also sees, just the turtle sees it later. Scrolling down to the bottom, we see that at iteration 36, the rabbit and the turtle are both looking at the same number. Namely, they're both looking at the number 1006. Remember, the reason why there's an 1006, by the way, is just that I rounded up to the next prime from 1,000, just to make it so that my function, which was send something to x squared plus 1 or whatever, didn't accidentally run into any problems because of the Chinese remainder theorem and that kind of thing. So 36 iterations later, we have found this match. And so what's being remarked here in the output is that the 36th step and the 72nd step of our path are equal. And that is what we found with this algorithm. Now, just to compare that to what we actually could have found, I also had my program find the first collision. That is the very first time that there's a pair of numbers on the path that are equal. And in this case, that happens to be that the 28th step and the 38th step are actually the same. We didn't find that out until we'd taken 72 steps. But as promised, the 72 steps that we did take was less than double the best possible answer. And that's the promise here. We're always going to find not the first collision, but we're going to find a collision in at most twice as many steps as when the first collision actually shows up. Here's another example. In this one, we got really unlucky. So note the first actual collision was between step 18 and step 101. So that is to say, the first actual collision was very, very far down the path. But then we didn't actually find that collision until the rabbit was 164 steps down the path. But note we only needed to do 82 comparisons in total in order to find this. So we have reduced drastically the number of comparisons that we're doing in order to actually find this collision. And another example, just so that you can see this. Again, feel free to play around with this. Like before, if you want to do a bunch of these all at once, you're welcome to do that. So here I'll go ahead and pull up a size 1,000,000 instead of size 1,000, and you can see how many comparisons it is taking to find this collision. And you can see it's often taking between 500 and 1,500 comparisons to find our first collision. And again, the real point here is that 500 and 1,500 are both way smaller than 1,000,000. So I'm having to do a lot less work to find this collision than you might at first expect. And I'm not having to do an awful lot of comparisons like we were the way we were doing this back with the birthday algorithm before this. Okay, so now that we hopefully understand how Pollard row makes finding collisions easier, let's talk about how finding collisions helps us factor and how finding collisions helps us calculate discrete logs.